Assignment 1W, Rational Functions and Wholes. The learning objective for this assignment is similar to the previous assignment. We are going to be using the limit notation to describe what functions do as we get closer and closer to the whole. Let's start with example 1. As can be seen here on the graph, we clearly have a whole when x is equal to 3. Now, how am I going to write the limit notation for this? Well, what I'm going to do is I'm going to zoom in on the whole so that we can look at it more closely. I see that the y value that would have been there is 1. So now writing the limit notation, as x approaches 3 from the left side, and let me add 3 minus and 3 plus here to remind you what that means. 3 minus means slightly to the left of 3, and 3 plus means slightly to the right of 3. As I approach the whole from the left, and also as I approach the whole from the right, we actually are approaching the same value of 1, but the function does not equal 1 there. It only approaches it as we get closer to that point. So we're approaching 1, but not ever equaling 1. Now, since my limit approaches 1 from both the left side and the right side, I can actually just write the limit as x approaches 3 of the function is equal to 1. Let me be clear about something, and maybe this is the mathematician inside of me. We are not saying that the function equals 1 at this place, because the function has no value there. We're just saying that the value approaches 1 as we approach that whole from both sides. Example 2 is going to require some more thinking, as they gave us the two polynomials in the rational function as standard form. We're going to factor them so that we can easily identify the wholes. Also notice the top part can be factored by factoring out the 10. That helps us realize that the x plus 3 factor is going to cancel out. That means that x equals negative 3 is going to be a whole. We now know there is an asymptote at 2 because of the denominator factor right here. So I'm going to add the asymptote. Looking at the standard forms again, which is very useful for determining the end behavior, I notice that the degree on bottom is bigger. So bigger on bottom means 0. The denominator wins. So the end behavior of my graph is going to approach the x-axis. Plugging in positive values, I can get this curve there to the right of the asymptote. Let's figure out where the whole would have been. To do that, we're going to use our new formula after the crossouts have already been performed, which is 10 over x minus 2. I can plug in negative 3 into that formula. It won't cause a division by 0. 10 divided by negative 5 is negative 2. Don't be fooled by this. Just because I can plug it into the new formula does not mean I can plug it into my original formula. So when I say that x equals negative 3 creates a y value of negative 2, I'm actually saying that there's a whole here. I can also quickly identify the y-intercept by plugging in x equals 0 and kind of connecting those dots with the curve. And now I'm doing the task that was asked for me, which was to find the limit notation of the whole. As you can see here, from the left side, my function's approaching that negative 2, and from the right side, it's approaching negative 2. So it's the same from the left and right, and that's normally with all wholes. So therefore, the limit as x approaches negative 3 of my function is negative 2. You can also do this by adding tables, and you can do this in Desmos. Now, when you plot these things in Desmos, you're not going to see the whole blatantly there. However, if I put my cursor on it and go up to the whole, you're going to notice that it creates a whole when I hover over x equals negative 3. And you're going to notice that the y value is not negative 2, it's undefined there. So let's create the table that approaches negative 3. I'm going to create my table, and as you can see here, that I have an undefined at 2 because there's an asymptote there. I'm going to change the x values. I've created my table. I did it to where you can see both to the left and the right of the function with numbers that increasingly get closer and closer to negative 3, that our y values are getting closer and closer to negative 2 without ever actually equaling negative 2 when x equals negative 3. So filling out these tables, you can see the clear pattern that as I get closer to -3 on the x, my function gets closer to -2 in both tables. All right, example 3. Sometimes when you have rational functions, they're going to look like normal parabolas, like in Algebra 2 or Algebra 1. But don't be fooled. There might be a hole. You have to be careful with it. Here we have a hole at x equals 1. In this particular case, you cannot factor this with normal integers, so you can just use the graphing calculator to get this. And you're going to notice that there's a hole right here above x equals 1. I'm going to write the limit for this hole right here, and I see that as I get closer to 1 from both the left and the right of the hole, that I'm approaching the value 5. All right, let's do our final example for this video. We have a rational function named h. The top part's factored, the bottom part is not factored. Let's factor the bottom part and also expand the top part. And I'm going to notice that I have a hole where these two factors cancel out. And that means I have a hole at x equals 2. In the denominator, I have x plus 6, so that means I'm going to have a vertical asymptote at x equals -6. With the hole and the vertical asymptote identified, I can now know my domain. I know that x can't equal -6 because of the asymptote, and x cannot equal 2 because of the hole. If I want to write that in interval notation, I would do it as such. Because the degree in the top part of the polynomial is squared, and the degree in the bottom part is squared, that is each the same, divide the coefficients, and dividing the leading coefficients of these terms right here is 1 divided by 1, so we're going to have a horizontal asymptote at y equals 1. Now, what about the zeros? Well, this is why we're doing this example. You got to be careful. You might say, hey, x minus 2 equals 0. That means I have a 0 at x equals 2. But, as been stated in the domain, x equal 2 is not in my domain. Therefore, there is a hole where there is supposed to be a 0. So the correct answer for this is there are no zeros. And for the end behavior, since I've already identified the horizontal asymptote, I take the limit to infinity and I get a value of 1. And there you go. You can see here in the graph that right there, you would think there would be a 0. And when you look at Desmos, it looks like there's a 0 there. But if you actually hover over it, it's undefined there. That's not a 0. So this function literally has no zeros.